Last time we talked about the eigenvalue method. So this is a case of how do you approach a problem of the form x prime equals ax, where A is a matrix with numbers. It's essentially the constant coefficient, if you will, for systems of equations. And we saw that there is a method. So what do? Step one, find the eigenvalues, and we call those the lambdas. Now, how do you find those? Well, what we do is we find the determinant of a minus lambda I, and we set that equal to 0. So this is really a polynomial in lambda. And so when we talk about finding the eigenvalues, we're talking about finding the roots of a polynomial. Algebra. So, all right, great. So we found our eigenvalues. Now, what's next? If possible, you'll notice here there's an asterisk. What is that? Well, not all matrices have a nice complete set of eigenvectors. Sometimes you will come up short. Okay, so what happens then? Well, great question. We'll talk about that in our next meeting. But for now, let's just say, okay, find, if possible, the n linearly independent eigenvectors. Now, there's again, if you're wondering, wait, how do I know if they're linearly independent? You can always just check the Wronskian. But here's a nice simple fact. If the eigenvectors come from different eigenvalues, no doubt, no doubt. So actually, we won't worry about the Wronskian very often. Just the process naturally gives us our linear independence. All right, now remember, how do you find these? What does it mean to find an eigenvector? Well, we want A times a vector is lambda times that vector. So in fact, the word eigen in eigenvector says, oh, we're making the same vector. See how we have the same vector on both sides. So somehow, when you carry out this matrix multiplication, you're getting to a point where you say, what direction, because the vector represents a direction, is more or less being preserved. That's the idea. Now, how do you actually do that, right? Because it says find it, but how do you find it? Well, you come to this matrix, A minus lambda I. And now you know what lambda is. So this is actually a matrix with numbers. And you say, all right, what do I need to multiply it by to get 0? Now, you might say, wait, what? You had 0 before. But be careful here. This 0 is a number, whereas this 0 here is a vector. So now you have to just fill that in. And oftentimes you can do it by eyeballing it. For 2x2s, there's a quick way to do it, if you're not sure, which is to take a row and you say, okay, write it backwards, and then flip a sign on one of the terms. Not on both, just on one. And you're done. If in doubt, just check the multiplication, and do you get the 0 vector out? All right, now, why were we finding these eigenvalues and eigenvectors? Well, because eigenvalues, eigenvectors lead to solutions. Namely, you have E eigenvalue t times eigenvector. We say, we just found a bunch of solutions. And now, superposition. So we can take a linear combination of those solutions, and if we've gone a full set of eigenvectors, we've succeeded. Woohoo! Success! And so we have solved our system. So that's the idea. That's the idea. So, all right, let's try it out a little bit. So let's look at the following example. Use the eigenvalue method to solve the system x prime equals 4x plus y prime equals 6x minus y, x of 0 is 5, and y of 0 is minus 2. All right, now we know what we're going to do here, because it says use the eigenvalue method. So we're like, cool, we're going to do that. And now you might say, wait a second, we have a problem. What's our problem? Well, the eigenvalue method has matrices, right? Because eigenvalue, eigenvectors, that's always in reference to a matrix. There's no matrix in this problem. Or is there? So here's the thing. We can rewrite the problem in a matrixy type way. So here's the way it's been written. X prime is 4x plus y, and y prime is 6x minus y. So that's our system. And we can rewrite this as x, y prime. Okay, that's the left-hand side. So we're combining it into sort of one single equation. And now we grab the coefficients, 4, 1, 6, minus 1, and x, y. Okay, now we have our setup. Good, a matrix has appeared. Okay, so what do we have? Well, what we can think of is that this matrix here, this is our A, and we're going to represent this as our X. Now, you might say, wait, you mean that X? No, technically it's a bold X, but we oftentimes won't bold it as much as we should, but it's the vector. Okay, so now we're ready. We've written it in a way where we can use our method. In other words, we've written it using a matrix. So, first step, what are the eigenvalues? So we want to take the determinant of A minus lambda I. Now, when we talk about A minus lambda I, we're really saying you take your matrix A and on the diagonal terms, subtract lambda. So you'll have 4 minus lambda, 1, 6, minus 1 minus lambda. All right? So A, subtract lambda I, means subtract lambda on the diagonals. Now we take our determinant. This will be down diagonal. We have 4 minus lambda times minus 1 minus lambda. Subtract the up diagonal, 6, 1. All right, so this is minus 4 lambda plus lambda squared. And then we have minus 6. Well, all right, that would be what? Lambda squared minus 3 lambda minus 10. All right, great, wonderful. We have our polynomial. Now remember, what are we doing? We're setting this to 0. All right, well, what do? Well, we multiply. Okay, so, sorry, I said multiply, but we factor. So this becomes what? Well, we want two things that multiply to negative 10 and add to negative 3. So we could do lambda minus 5, lambda plus 2. Let's check. Lambda squared, good. 2 lambda minus 5 lambda, minus 3 lambda, great. Minus 10, wonderful, wonderful. Okay, so our eigenvalues are 5 and negative 2. Good. Now, we're more or less about halfway. So we found the eigenvalues. Now we need to do eigenvectors. Okay, so what do? Well, we'll give ourselves a little bit of space here. And we'll say, well, let's start with the eigenvalue of 5. So I'm going to look at A minus 5i. So I'm going to come here and think about putting in lambda for 5. So I get minus 1, 1, 6, minus 6. And I want to find some vector so that when we multiply, we get out 0, 0. So the goal here is to say, what's in the box? What's in the box? All right? What goes here? Can you spot a vector that works? Well, sometimes you can just eyeball it and say, I see something. And if you can't, you can use the rows. But actually, this one's pretty easy to spot. 1, 1 does the job. All right, so there's our eigenvector. Okay, well, that was for lambda equals 5. What about for lambda equals minus 2? Well, okay, so again, I'm just going to use this to Q off of. I'm putting in lambda equals minus 2. So 4 minus minus 2, so be careful. They can be a little funny. So 6, 1. And then here, we'll have 6. And minus 1 minus minus 2 is 1. Okay, good. And we want to get out 0, 0. Now, do you see something that works? Well, if you don't, we can just do the following. Pick a row. It doesn't matter in this case. All right, the first row. All right, great. Now I'm going to write it in backwards order. See how 6, 1, 1, 6. And now I'll flip a sign. Doesn't matter which one. I can flip the sign in the first term. Minus 1, 6. And I claim it works. Why? Check it. Minus 6 plus 6, 0. Minus 6 plus 6, 0. Success. Kapla. Which, of course, we all know is Klingon for success. All right. So now we've gotten our eigenvectors. So we found our eigenvalues, we found our eigenvectors, and we're ready to say, what does a solution look like? Well, a solution to this form has the following. Namely, it'll look like x equals some constant, and then e to the eigenvalue t, so I'm using 5, times eigenvector, plus some other constant, e eigenvalue t times eigenvector. And good, done. Now, note we have initial conditions. Okay, so we can do one of two things. We can unravel now, solve for initial conditions, or we can solve for initial conditions and unravel. We will need to do both things. So let's solve for initial conditions now, just so we get used to it. So what would our initial conditions look like? Well, coming up here, what we would have is we say, well, what is x of 0? It is the function little x0, little y0, and that would be 5 minus 2. Now you might say, whoa, wait, those were our eigenvalues. Coincidence, coincidence. That's what that is. Don't read too much into coincidences. Okay, so, excuse me. So now we plug in 0. So x of 0, which is 5 negative 2, right? That's what we did here. So that equals, now e to the 0 is always 1. So that's some constant c, 1, 1, plus a constant d, minus 1, 6. Now, if you rewrite this, excuse me, if you rewrite this, sorry, what do we have? Well, reading the top entries, 5 is equal to c plus d times minus 1. So, whoops, let's write that as 5 equals c minus d. That looks a little bit better. Minus 2 is equal to c plus 6 times d. And what can we do? Well, let's cancel the c's. So, do a quick subtraction. 5 minus minus 2 is a 7. C minus c, 0. Minus d minus 6d, minus 7d. Well, that tells us that what? Well, it tells us about d. D needs to be negative 1. But now that we know what d is, we can plug in. Say, oh, well, 5 has to equal c minus d, so that's c plus 1. So that tells us that, oh, c is 4. Well, great. Now we know c and d. So we're in our home stretch. Here we go. We have our solution x looks like c, which is 4, e to the 5t, 1, 1. And then plus d, which is a minus e to the minus 2t, minus 1, 6. All right. Now, is this our answer? And why not? It's not our answer. Why not? Well, because the matrix form wasn't part of the problem. We introduced it. So we should unintroduce it, get back to what it is. So how do we do that? Well, we said, well, look, this x, it's really, another way to write that is our x, y. And this is what we're after here. So we read off the rows. So you can say, okay, so we have that little x. We read off the top. That's 4 e to the 5t minus minus makes a plus e to the minus 2t. And then y, well, okay, read along the bottom. 4 e to the 5t and minus 6 e to the minus 2t. And now we're done. There's our solution to our system. All right? Not too bad, right? There's a couple steps, but we've broken it down into sort of manageable things. We have our find eigenvalues, find eigenvectors, and then we had solve for initial conditions if needed, and unravel. Each step, not too bad. And we can do this. And we will. We're going to be doing this a lot in the next few weeks. And of course, maybe we'll even be tested on these things. When we thought about solving constant coefficients, we said, okay, once we had the basic idea down, then we had to deal with two issues. Now, the first issue we dealt with was, how do we deal with complex roots? And the second was, how do we deal with repeated roots? So repeated roots, we're holding off that discussion, so let's get complex. So we have a nice basic fact, namely, if you have a matrix and the numbers are real, so we're keeping it real, it's possible to have complex eigenvalues. And we've seen that before. If we have a polynomial, we can have complex roots, even though all the numbers involved are real numbers. So, okay, what do we do? Well, if that does happen, that we have complex eigenvalues, well, then it turns out there's this beautiful fact that the eigenvalues occur in conjugate pairs. So in other words, if I have a plus bi, I also have a minus bi. So it's like you flip the sign for the part which has the I on it. But not only do the eigenvalues have this nice pairing, the eigenvectors have a nice pairing as well. So let's see an example of this. So here we go. Verify that 1 plus 2i is an eigenvalue of the matrix 7, 4, minus 10, minus 5 with this eigenvector 2 and negative 3 plus I. Also, give the other eigenvalue an eigenvector. Okay, so now you might say, what does it mean by the other? Well, it's a 2 by 2 matrix, so there should be 2 eigenvalues. And each one should, if we've lived a good, clean algebra life, should have its own eigenvector. Okay, so we see the word verify. That's usually a pretty good word. What does it mean? It means we don't have to go through the whole process of finding. It means we have to go through the process of checking. So we want to check that what we think should be true is true. So what is the test for eigenvalues and eigenvectors? Well, we say, what does it mean to be an eigenvalue eigenvector? It means that we should have A times V should equal lambda times V. And now we say, okay, well, where are our pieces at in this case? Well, our matrix, that's our A. Our vector, that's our V. And this 1 plus 2i, that's our lambda. So we need to check, does A times V equal lambda times V? So let's check. We have two sides to work out. All right, so here we go. A times V. We'll start with the left-hand side. That's 7, 4, minus 10, minus 5. And we're going to multiply this by 2, minus 3 plus I. All right, so matrix multiplication. You go along the row while you're going down the column. 7 times 2, 14. 4 times minus 3 plus I. Well, let's just write that as 4 times minus 3 plus I. We'll come back and simplify that in a second. All right, 2 times negative 10, negative 20. Negative 5 times 3 plus I. Well, again, we'll go ahead and work on that in a second. All right, well, it's been a second, so let's work on that. Okay, so what do we have? Well, we have 14 here. Distribute the 4 through. So minus 12 plus 4I. Downstairs, minus 20. Minus 5 times minus 3 plus 15. Minus 5 times I is minus 5I. So 14 minus 12 makes a 2. Then we have a plus 4I. Minus 20 plus 15 makes a minus 5. And then we have minus 5I. All right, that's the left-hand side. All right, now we're going to do the right-hand side. Lambda times V. Well, so we're going to take 1 plus 2I times 2 negative 3 plus I. So here we have a number in front. It's like we're scaling because we're scaling. And so what does that mean? It means you multiply each entry times that value. So it's 1 plus 2I times 2. And it's 1 plus 2I times minus 3 plus I. Okay, so 1 plus 2I times 2. Well, okay, so that would be 2 plus 4I. All right, well, that's looking promising. Now here, what do? Well, you FOIL. 1 times minus 3, minus 3. 1 times plus I, plus I. 2I minus 3, minus 6I. 2I times I, 2I squared, also known as minus 2. Put it together. Well, upstairs, 2 plus 4I. Minus 3 minus 2 is minus 5. I minus 6I is minus 5I. And now, our grand test, do they match? And they do! Woohoo! Or, as you might say, wow! That's a cool. All right, so, verify. Done. Nice. Now, we're not finished with the problem. We finished the first sentence. It says also give the other eigenvalue and eigenvector. So how do we do it? Well, we could, again, go through a long process, but that sounds like work. That's not what we want to do. So what are we going to do? Well, we're going to say we have this fact. Conjugate pairs. So, say, all right, our other eigenvalue is we take our 1 plus 2I, and anything with an I, you flip the sign. So instead of 1 plus 2I, what do we have? 1 minus 2I. All right, great. What about our eigenvector? Okay, same idea. So look at your vector. Anywhere where you see an I, flip the sign. Well, it's just one I, so we would have 2 minus 3 minus I. And done. So that's it. That's it. Nothing more complicated than just remembering you have to flip the sign. And in fact, what we're going to see is in practice, we usually only even find one eigenvector because we say, look, we already know what the other one is because, you know, we have a plan. So what's our plan? Now think back to when we did constant coefficients, just normal differential equations. what happened when we had those complex roots? Well, what we did is we said, by combining the pairs, we can hide the complex part. And so now, instead of having an exponential function, we also had an exponential function in sines and cosines. So the sines and cosines were sort of where we hid the complex part. And we're going to do it again. So what goes on? Well, if we have the situation where we have our x prime equals ax, so we're in our first order linear system, our entries of a are real. We're keeping it real. Good. And we have an eigenvalue which is complex. So alpha plus I beta. Well, then it also has an eigenvector, and that eigenvector will also be complex. It has to be. Has to be. And so we'll write that as a plus ib. So essentially, you can think of it as we're taking our eigenvector and we're splitting it into two parts. And in one part, a, that's the real part. And in the other part, we say, okay, this would be all the parts which had I, but since everything has an I, you can pull it on front. So it's a plus ib. So we're splitting up our eigenvector. Now, we still have the philosophy. It hasn't changed. It says, oh, well, what do we do? We have e eigenvalue t eigenvector. Well, but we know how to rewrite e to the alpha plus I beta t. That's e to the alpha t cosine beta t plus I e to the alpha t sine beta t times a plus ib. Now, if we write that out, and so we'll do that. It's good to work through this once in your life, and we'll actually have to work through this a few times, but here we go. So we have, if you look at it, we have this expression, and what do you want to do? Well, it looks like we should FOIL. So what are we going to do? We're going to FOIL. All right, so let's think about how could I end up with something which is real, no I. Well, one thing is I could take e to the alpha t cosine beta t, think of this as our function scalar, and here's vector. Okay, so for our real part, we have e to the alpha t cosine beta t a. Now there's another way to get a real part, which is to do that. Namely, combine the two parts attached to I. Because what will happen? Well, you'll have an I squared. And what if you have an I squared, that turns into a minus. And the I goes away. So you have a minus e to the alpha t sine beta t times b. Okay, so expanding, that's your real part. Now, what else do we have? Well, we also will have our imaginary part. Now, how do we do that? Well, we take the outer parts and multiplying. That would give us what? E to the alpha t cosine beta t times b. And then we take our inner parts. And that would be a plus our e to the alpha t sine beta t times a. And now, here's the punchline. Think back to constant coefficient, differential equations. We said, oh, we split it into the real part and the imaginary part, and those became our solutions. Same idea. So our real part is a solution, and our imaginary part is a solution. Now, how did that happen? Well, remember how we said things come in conjugate pairs? That's how it happened. Because what you'll do is when you expand things in the conjugate pairs, you'll get real part plus imaginary part in one case, real part minus imaginary part in the other case, and then by combining, you can cancel out. And so we say, beautiful. And what do you notice? The a and the b, by construction, they don't have any i's in them. Neither do these functions, e to the alpha t cosine beta t or e to the alpha t sine beta t. So now everything looks beautiful. It looks like something that you'd take home to meet your family. Say, look, there's nothing imaginary here. It's all good. It's all wonderful. Okay, so again, we have a plan. Complex eigenvalues, we say, great. We have the part coming from the eigenvalue, part coming from the eigenvector, expand out, get the real part, get the imaginary part. Those are our new solutions, and then life is good. So let's try it. Here we go. Solve x prime equals 7, 4, minus 10, minus 5x. And we have some initial conditions. X of 0 is 10 minus 8. All right, so what do we do? What do we do? Well, let's run through the process. Now, we kind of know complex things are coming, but we may not know on a test beforehand. So we're not going to put ourselves in the complex mindset yet. We just say, look, find eigenvalues. That's our first step. All right, so here we go. Find our eigenvalues. Well, it's the same process. And so we're going to take our determinant of a minus lambda I. And so this becomes 7 minus lambda, 4 minus 10, minus 5 minus lambda. All right, well, this is what? 7 minus lambda, minus 5 minus lambda. Then we're going to subtract, right, go down the diagonal, subtract up the diagonal. Negative 10 times 4. Well, 7 times negative 5 is negative 35. Then we have 7 times minus lambda, minus 7 lambda, minus lambda times minus 5, plus 5 lambda, and of course don't forget the lambda squared. And then minus 40 makes a plus 40. All right, so that gives us lambda squared, minus 7 lambda plus 5 lambda, minus 2 lambda. Minus 35 plus 40 is plus 5. All right, well, that doesn't look too harmless. All right, so we set this equal to 0, and we find the roots. All right, we try to factor. We try harder. We try the hardest we possibly can. All right, we fail, but that's okay. Now we can do completing the square, or we can do quadratic formula. Let's do the quadratic formula. I think I may have tried too hard to factor on that one, but that's all right. Here we go, quadratic formula. So lambda is negative b, 2, plus minus the square root of b squared, 4 minus 4ac, 4 times 1 times 5, all over 2a. All right? Well, that would be 2 plus minus 4 minus 20 is negative 16. Square root of a negative will give us an I, and then square root of 16 is a 4. And so we have 1 plus minus 2i. In case you're wondering what would have been the completing the square method, because, maybe you wonder, we have time. Let's do it really quick. What you do is you say, okay, here we start by writing down lambda squared minus 2 lambda. And you say, what would I need to complete the square? A plus 1, right? Minus 2, divide that by 2 is minus 1 squared plus 1. And then, of course, you add 4. And you say, oh, well, that's the same as you do the square part. Lambda minus 1 squared is equal to minus 4. Now, take a square root, and you say, oh, that's the same as lambda minus 1 is square root of negative 4 plus minus 2i. and which gets you to 1 plus minus 2i. All right, so eigenvalues are done. We got complex eigenvalues. We knew it was going to happen, but still, it warms the soul that it happened, because that means we're on the right track. Okay, what comes next? Now, the answer is not eigenvectors, it's eigenvector. We only need one. Isn't that cool? When it's complex, you only have to find one eigenvector. Well, don't worry, there's a trade-off coming, and we'll see the trade-off in a second. All right, so what do? We're going to take our A minus lambda I. So we want to be very explicit about which eigenvalue we're using here. So I'm going to use 1 plus 2i. All right, so this would be 7 subtract 1 plus 2i, 4 minus 10 minus 5 subtract 1 plus 2i. All right, now if you clean this up, you can distribute the minus through. So this would give you a 6 minus 2i, a 4, a minus 10, minus 5, minus 1, makes it minus 6 minus 2i. All right, good? Got that? All right. Well, now what? Well, the next thing is to say, okay, what is our eigenvector? Well, so we want to find our eigenvector to get 0, 0. And this is when it looks like, uh-oh, we're in trouble. How do you find something complicated? Well, the answer is we use our technique, right? So what was our technique? Well, our technique said, do the following, pick a column. Doesn't matter which column. Sorry, not pick a column, pick a row. Pick a row, pick that row. Copy it down backwards. All right, 4, 6 minus 2i, flip a sign. Okay, there we go. And done. We found our eigenvector. See, isn't it nice to have that tool? Now you might say, wait, is it really? Well, yeah, you can. Multiply it out and check. So you have here, minus 4 times 6 minus 2i, plus 4 times 6 minus 2i, that's easy. Minus 10 times minus 4 is 40. Now if you take minus 6 minus 2i, times it by 6 minus 2i, what will happen is you'll get minus 40. There's some work to be done, but it does work out. All right, so now this is an eigenvector. You can always clean it up. Now, what do we mean by clean up? I'd say if you see anything common, go ahead and pull it out. So let's see, they're all even numbers. Let's go ahead and pull out a 2. And I see lots of negatives. Let's pull out a minus 2. And so if we do that, we would have a 2 and a minus 3 plus I. They're both correct. So eigenvectors aren't unique. You can always scale. We talked about this in our last meeting. All right, so now what do we do? Well, now we say, how do we use this one eigenvector to find our two solutions? Well, here we go. We do the following. We take our eigenvector, and now what we're going to do, let's do it here, is we're going to pull it apart. And the way we pull it apart is to say, what's the real part? What's the imaginary part? So the real part says, look for things without i's. Well, 2 and negative 3. Now, what about the parts with the i's? Well, there's nothing here, so that means there's nothing. We put 0. And here, 1. And we've pulled the I out in front. So that's pulling the eigenvector apart. All right, so here we go. We're going to take our e to the 1 plus 2i t times our eigenvector pulled apart. But, of course, what we really do is we rewrite this part. So this is the same as e to the t cosine 2t, and plus e to the t sine 2t, and then I forgot an I e to the t sine 2t. Okay, that's the first part, times 2 minus 3 plus I, 0, 1. So here, I'm just rederiving it. You could memorize the formula, but that sounds dangerous because it's easy to sort of swap things. And I don't want to make mistakes. My goal is to try to get the right answers and be able to be okay. All right, so we're going to do the real parts by, we take real, imaginary. So we have e t cosine 2t, 2 negative 3. And then when you multiply the imaginary parts, you'll get I squared, which is a minus e t sine 2t. And that is times 0, 1. Okay, so this is solution number 1. Now we'll do something similar and for our imaginary parts. All right, let me grab an appropriate color. Let's see. We'll do the outermost, and so we'll get a I, and we'll have e t cosine 2t times 0, 1. And then we're going to also have a in plus e t sine 2t 2 minus 3. All right, so here's solution number 2. Okay, so we found our 2 solutions. Good. Are we done? Well, not quite. Right? Because what do we need to do? Well, we need to put those together, and we haven't even tackled initial conditions yet, and we've run out of paper. That's okay. We always have more. All right. So I'm going to move this up for just a moment here so we can copy. So those are our 2 solutions. So we get the following, namely that x is some constant c times e to the t cosine 2t 2 negative 3 minus e to the t sine of 2t 0, 1 plus some constant d e to the t cosine 2t times 0, 1 plus e to the t sine of 2t times 2 minus 3. All right, there we go. So, putting this up here. So we did all our work to say this is the general form for solutions. Now, we're not after the general form. It's a useful tool. We're after a very specific solution, and namely the one where x of 0 is 10 negative 8. So what comes next? We're going to plug in 0 and then solve for c and d. So here we go. So x of 0, which is 10 negative 8, is equal to, now the nice thing, e to the 0 is 1, cosine of 0 is 1, sine of 0 is 0. So a lot of things go away. So you have 1 times 2 negative 3. 1 times 0 times 0, 1, well, goes away. Plus d, 1 times 0, 1. And then 1 times 0 times 2 minus 3 goes away. All right, so that leaves us with the following equations, right? Read off the top entries. 10 is equal to 2c, and that's that. And then minus 8 is equal to minus 3c plus d. Well, we're in luck. 10 is 2 times c. So that tells us c has to be 5. Okay, so then minus 8 equals minus 15 plus d. Add 15 to both sides. That tells us d is 7. All right, so now we can plug it in. And we're going to get the following. X is equal to 5 e to the t cosine 2t, 2 negative 3, minus e to the t sine of 2t, 0, 1, plus 7, and then we have e to the t cosine 2t, 0, 1, plus e to the t sine 2t, 2, negative 3. Now, this is the correct answer, and I'm going to go ahead and box it because, well, I started boxing it. But we can clean it up a little bit. And how do we do that? Well, let's just mush it all into one formula. Okay, so we could also say that x is equal to. So 5 e to the t cosine 2t times 2 makes 10 e to the t cosine 2t. 5 times minus 1 e to the t sine 2t times 0. Okay, that's 0. 7 e to the t cosine 2t times 0 is 0. And then we have 7 times e to the t sine 2t times 2. Well, that makes a 14 e to the t sine 2t. All right, now the bottoms. 5 e to the t cosine 2t times minus 3 is minus 15 e to the t cosine 2t. Boom, boom, boom. 5 minus e to the t sine 2t times 1 makes minus 5 e to the t sine 2t. Then we have 7 e to the t cosine 2t times 1. So that's plus 7 e to the t cosine 2t. Then 7 e to the t sine 2t times minus 3 makes minus 21 e to the t sine 2t. Now, there's not a lot you can do upstairs. So we have 10 e to the t cosine 2t plus 14 e to the t sine of 2t. But downstairs, we can do some things. Namely, we can combine. See how we have minus 15 e to the t cosine 2t plus 7 e to the t cosine 2t? That makes it a minus 8 e to the t cosine 2t. And then minus 5 e to the t sine 2t minus 21 e to the t sine 2t makes it very negative, but it's a minus 26 e to the t sine 2t. And that's another way to write the answer. Wow! 2 ways? Yes. Which one gets points? They both do. Unless, of course, there's an explicit instruction to do one over the other. All right. Well, that's it for complex. And, of course, practice, right? Practice, practice, practice. And after a little bit of practice, it'll become second nature. Life will be good. Life will be wonderful. See you again. Bye.